Okay, just one more video we have regarding Fourier approximations, and some of you have wondered when you can use the variable j for an integration variable, and just to give you some heuristics in terms of when you can use j and when you cannot. Okay, let's say that where you can use the variable j. Okay, say we have we're looking for the Fourier approximation, okay, where we have f of x is equal to x squared, and the interval we have going from 0 to 2 pi, and we'll be looking at a third order Fourier approximation. Okay, so we have for a naught, okay, going to have 1 over pi times the integral as x goes from 0 to 2 pi of f of x dx, where f of x we have at x squared, and for the antiderivative of x squared, we have x cubed over 3. And so for the integral, so we got 1 over pi times the cube of x over 3 as x goes from 0 to 2 pi. Now the cube of 2 pi, okay, that is going to be 8 pi cubed. And we have this over 3 and dividing by pi. So we have the simplification at 8 pi squared all over 3. So that is going to be the a naught. Now, looking at what we have for f of x times the cosine of jx dx. Now, if we look for the general integral, okay, say we have for x squared times the cosine of jx dx. So we are looking at repeating integration by parts. So we have letting u be equal to x squared, and we'll have for the differential relation that results, we're going to have du is equal to 2x dx. And setting dv to the cosine of jx dx, we have the antiderivative will be 1 over j times the sine of jx. And looking at what we have for u times v minus the integral of v du. Okay, so we have x squared over j sine of jx, and we have for the minus integral of v du, so just dragging out the 2 over j, and we have inside leaving x and the sine of jx dx. And again, for the next round of integration by parts, so setting u equal to x, we have that du is equal to dx, and letting dv be equal to the sine of jx dx, we have the antiderivative v is equal to negative 1 over j times the cosine of jx. And bringing down again the first antiderivative, and we have for the next set of terms, we have negative 2 over j times u times v, resulting in positive 2 over j squared x times the cosine of jx. And then we have minus, okay, what is going to be 2 over j squared. Again, that's negative 2 over j times what we have for the subtraction of the integral of v du. Okay, and so in this particular case, all right, so we have minus 2 over j squared times the integral of the cosine of jx dx. And we have expanding, we have these three terms, okay, with x squared over j sine of jx plus 2 over j squared x cosine of jx minus 2 over j cubed times the sine of jx. And for what we have in terms of j, okay, so you have all three of these ratios will be defined for all real numbers. Or I should say, not all real numbers, but all natural numbers. Natural numbers being the counting numbers starting with 1. And so for what we have for a sub j, okay, and for any natural number j, okay, so we have 1 over pi times the integral as x goes from 0 to 2 pi, so we have x squared times the cosine of jx dx. So we've got 1 over pi, and again we have this set of antiderivatives with, again, x going from 0 to 2 pi. And again, we had the sine of 2 pi is going to be negligible, and the cosine of 2 pi is going to be 1. So you're looking at, in this set, at both 0 and 2 pi, you're going to have only what we have for the middle term, okay, with x at 2 pi, where we're going to have 1 over pi times, okay, and we have 2 times 2 pi is 4 pi, and you got what's going to be the cosine of 2 pi j all over j squared, and we have in cross multiplying. So you got pi's will go out. Cosine of 2 pi is going to be fixed at 1, and 2 pi times the natural number, the cosine is always going to stay at 1. So you're looking at 1 times 4 over j squared. And we have with j at 1, we're going to have a sub 1 at 4, and a sub 2 will be 4 over 2 squared, which is 1. A sub 3 will be 4 over 3 squared, which will translate to 4/9. And if I were to go any further, so it would have like a sub 4 is equal to 1/4. And just taking what we have for, let's say for the integral of x squared times the sine of jx dx, again, we're going to have repeating integration by parts. And for what we have in this particular case, all right, so we got u is equal to x squared, du is equal to 2x dx, dv is equal to the sine of jx, and the antiderivative we're going to have with v is equal to negative 1 over j times the cosine of jx. And for u times v, okay, so we have negative x squared over j cosine of jx, and for the subtraction of the integral of v du portion, and that's going to translate to 2 over j, the addition of 2 over j times the integral of x times the cosine of jx dx. And with the next round of integrating by parts, we got with u is equal to x, we lead up to, or we have arriving at du is equal to dx. And for the setup here and attain the antiderivative of dv is equal to the cosine of jx dx, we had that v is equal to 1 over j times the sine of jx. And following through, okay, so for the next set of antiderivative terms, so you're going to have 2 over j times what we have for u times v. So we have 2 over j squared times x times, okay, what is going to be the sine of jx. And we have minus, okay, again, for 2 over j times the subtraction of the integral of v du part, we land at 2 over j squared, or the subtraction 2 over j squared times the integral of the sine of jx dx. And we have in the follow through, okay, so we have these three terms to arrive with the third antiderivative at the addition of 2 over j cubed times the cosine of jx. And we can work with j for all natural numbers. And for what we have in the case of b sub j, okay, so we got 1 over pi times the integral as x goes from 0 to 2 pi of x squared sine of jx dx. And so we have with the antiderivatives as x goes from 0 to 2 pi, so we're going to have from the formula, so we got 1 over pi. And again, so we have at 2 pi and 0, okay, our sine term will automatically go to 0. And for what we have left standing at 2 pi, okay, so we have for negative x squared over j cosine of jx. At 2 pi, we have negative 4 pi squared over j, since the cosine of 2 pi goes to 1. And then we have at the upper limit 2 pi, you're going to have cosine of 2 pi is 1, and you have times 2 over j cubed. But at the end, at the lower limit, we're going to have the subtraction of 2 over j cubed. So you're going to have the only term left standing inside the bracket said negative 4 pi squared over j, and multiplying by the reciprocal of pi, so we have simplifying, so we have negative 4 pi over j. So you have b sub 1 is going to be negative 4 pi, b sub 2 is going to be negative 4 pi over 2, which will be negative 2 pi. B sub 3 is going to be negative 4/3 of pi. B sub 4 is equal to negative pi. And for what we have for g sub x, okay, and I decided to take this out to the fourth order, and in this capacity, okay, now your a naught was 8/3 of pi squared, and again, we're going to take half of this. So you got 4/3 of pi squared plus 4 cosine of x plus a cosine of 2x plus 4/9, so the cosine of 3x. And taking it out to the fourth order, so you have 1/4 of the cosine of 4x. And for what we have in the case of the sine terms, so we have from b sub 1, we have negative 4 pi sine of x. And in reference to b sub 2, so we have negative 2 pi sine of 2x. And from b sub 3, we have negative 4/3 pi of the sine of 3x. And finally, we have from b sub 4, we have negative pi times the sine of 4x. So we were able to utilize the integration with respect to the variable j. And where we might have this to be forbidden would be like if you had your function f of x equal to 2 times the sine of x times the cosine of x. Okay, now for the a naught, okay, this is not a problematic situation. That is going to go to 0. But once you start to look at multiplying this function by either sine of x, or I should say the cosine of jx or the sine of jx, and just for what we have, say if I were to take f of x times the cosine of jx and attempted to integrate with respect to the variable j, and so for 2 sine of x cosine of x times the cosine of jx dx, I have from 2 sine of x cosine of x, that is equal to the sine of 2x multiplying by the cosine of jx. And just from your sum and difference formulas, okay, we're going to have with the sine of 2x cosine of jx, we're going to have in one capacity, okay, we have one term resulting will be 1/2 of the sine of 2 plus j quantity times x. And we have with the other, we're going to have 1/2 of the sine of the angle where we had the quantity of 2 minus j times x, and integrating once you consolidate. Okay, so for 1/2 of the integral of the sine of the quantity of 2 plus j times x dx, we're going to have negative 1/2 of the reciprocal of 2 plus j times the cosine of 2 plus j x. And then we have with the other antiderivative, so we're going to have negative 1/2 of the reciprocal of 2 minus j times the cosine, where the angle we have at the quantity of 2 minus j times x. And if I combine these terms together, so we would have the negative of the quantity of 2 minus j, or you could say that as being j minus 2, and we have times the cosine of the quantity of 2 plus j times x, and then we have minus the quantity of 2 plus j times the cosine of 2 minus j times quantity times x. And notice in the denominator, so you have 2 all over 2 plus j quantity, and we have times the quantity of 2 minus j. And if I had just 2 and 2 plus j in the denominator, I could follow through and look for what we have for g of x through this pathway. However, we have 2 minus j in the denominator, and the ratio here is going to be undefined at j is equal to 2. So in this particular case, if you're looking like second order or higher, the integration through use of the variable j is going to be forbidden.